So good morning, everybody. I am François Paquet, the chairman of the task group providing dose coefficient. I am very pleased to welcome you today on this webinar. I will try to share my screen. I hope everybody can see my screen. So today we are having a webinar presenting a report on the production of dose coefficient for the assessment of internal exposure of workers and members of the public. This title is quite long, but what you have to keep in mind is maybe these four keywords, which are dose coefficient, internal exposure, workers, and members of the public. In fact, actually, this webinar will not be about the presentation of specific ICRP report. It will be more on presenting the work which has started about 20 years ago, which was about to revise the dose coefficient for the assessment of internal exposure of worker and member of the public. On this part of this work, a part has already been published. It has been published under the acronym OIR. OIR means occupational intake of radionuclides. So it's about the worker. So this part has already been published, and the work is still under progress for the member of the public. And this webinar will present what we have already published in the OIR series and what is currently being done for the public. So the program of this webinar, we thought it would be nice, before to start on what we have done, we thought it would be nice to have a small talk on the fundamental in internal dosimetry. In this talk, we will try to explain or to remind everybody how we derive dose coefficient, which parameters are used, which parameters are important for deriving and for producing dose coefficient, and that will be presented by Derek. Then I will try to explain the justification for producing new dose coefficient. We will have also a highlight by Demetrio on the new data which are used for the human respiratory tract model. Then we will have two examples of systemic model which are produced in our series with a specific focus on two elements which are important for radiological protection, which are iodine and cesium, that will be presented by Vladimir and by Rich. We will then have an answer of a question that I have every time I present this dose coefficient, which is about the difference which are between the new coefficient and the old coefficient that will be given by Tracy. We will have a small demo of the data viewer. The data viewer is a kind of software that you can download for free from the ICRP website. And so during this demo, you can either just listen to Vladimir, or you can also play by yourself. And if you want to do that, I can invite you to either to go to this link or to go to the ICRP webpage. On the tab, what we do, you will find publication. You can choose ICRP publication 151 and choose OIR electronic annexes, and then you will be able to download free of charge this viewer. So I let a few seconds for you to take the photography of this link if you want to download. Otherwise, you can just listen to Vladimir. And then we will have time for the question and the answer. So the webinar will be presented by this 6 or 7 speakers. What I would like to do is also to thank all the members of the TG95, which actively participate to the production of this dose coefficient. We are 14. It's a kind of small group, we have some room to invite many other people. If you want to join us at the end of this presentation, you will be welcome, because as you will see that it's a hard task to produce this model and dose coefficient. So this is, I'm finished for the introduction. I propose to stop and to give the floor directly to Derek to start with the fundamentals of internal dosimetry. Derek, you've got the floor.
Thank you so much, Francois. So we'll swap some screen sharing here. And really appreciate everyone joining us for this webinar. Thought it might be interesting to start with finding out a little bit more about who our audience is. So if you're willing, if you use either a web browser on your computer, or you can use your smart device and go to menti.com and enter that code, or you can use that QR code. And I'm going to ask a few polling questions of our audience just to get us started. I'll leave it on this slide just a few more seconds. Though as I go to the first question, these instructions are still going to be on the slide, so you'll be able to continue to join this group. See folks coming in, this is good. All right, so I'm going to go to the first question, and like I said, you can continue to join this group. But here's the first question for you, and you should be able to see it on your device, however you've joined. Really impressed by the number of participants this morning. This is a great turnout. Lots of folks that are interested in learning more about internal dose coefficients, and from a diverse set of workplaces, which is good. Okay, so here's my next question. So this is, you're just going to click on the map here, where you are. And if you're not happy with your first click, you can tap around before you hit the submit button. This is very cool. This is one of the things that, at least personally, I find very rewarding in getting to do work to support the ICRP. Okay, next question. How many years have you been working in radiation protection? Very nice. This is what I was hoping for with this audience. We are not a heavily biased audience in any direction in terms of years of experience. That's great. And hopefully we'll have something here for everyone. I know we have some attendees who are very much experts in internal dosimetry, and we also have attendees who are just getting started. So hopefully we've designed a webinar that will be valuable for everyone. Okay, and then Francois did a great job taking you through some of the topics. This is just a question to kind of pull, at least here at the beginning, your various interest levels in these topics. So this is just a scale. You indicate on a scale of 1 to 5 your interest in these topics. Though I must warn you, no matter what the results come back as right now, we're still giving you the same webinar. So you have absolutely no opportunity to influence the content by answering this question. What's rewarding is that these numbers are high for all areas. This is good. Okay, and here's my last question, and this is the first question I've asked that has a right answer, has a correct answer. So here's the question. We have a worker who inhales radioactive material at your facility. Which of the below describes the internal dose which should be assigned to that worker's record? So should we assign a committed effective dose, which the sex averaged reference person would have received if inhaling the same material as our worker? Or should we assign a committed effective dose which is specific to the sex of your worker? So if your worker is female, should we be assigning a female effective dose? If your worker's male, should we be assigning a male effective dose? Or should we be using as much worker-specific information as possible, only using reference data when information about the worker's not available? So, and you're not seeing answers coming in because I've hidden them. I'll show them to you here in a second. But one of the things I've noticed is when you ask a question that has a right answer, and people can see answers coming in, there's a bias that happens, right? People start to go where the majority is going. So we'll avoid that by hiding the answers here until enough folks have responded. Okay, so let's see those answers. So 65% of our audience thinks that we should be using as much worker-specific information as possible, right? 28% think sex averaged committed effective dose, and a smaller minority thinks let's use effective dose but make it sex specific. Okay, so I said there's a right answer. I'm going to tell you what the right answer is right now, and then we'll talk about the why a little later. So the right answer is the first one, if you're using the ICRP system of radiation protection. Okay, so like I said, I'm not going to explain it right now. We'll explain it here in a little bit. So I'm going to switch now. Stop sharing just for a moment and start this presentation. Okay, So let's get into the fundamentals. Thank you for taking the time to answer those polling questions. Those were very interesting. All right, so my task is to take us through the fundamentals associated with internal dose coefficients. And the goal is that when I'm done, you'll have confidence in the answers to these three questions. First, what is an internal dose coefficient? And specifically, we're going to focus on the committed effective dose coefficient. Then we'll go through how these coefficients are computed. And finally, I'll highlight some of the many improvements to the models and values informing these internal dose coefficients that you're going to hear more about those improvements from the other speakers as well. So in general, an internal dose coefficient gives the dose per unit activity taken into the body. And note that for inhalations, this term in the denominator needs to include the activity which is promptly exhaled. So if the radioactive material comes to the mouth or the nose, it counts toward the denominator, even if it very quickly goes back out. The idea behind the internal dose coefficient is to be useful to an operational dosimetrist. So in prospective radiation protection, the dosimetrist determines a potential intake scenario and multiplies that intake activity by the dose coefficient to give the dose to the reference person if it were in those exposure conditions, or the representative person if we're concerned about dose to the public. In retrospective dosimetry, the operational dosimetrist determines an estimate of an intake, perhaps based on bioassay data, and similarly couples that to the dose coefficient to determine the reference person's dose had it had the same intake as the worker. And an internal dose coefficient can be computed for any of these quantities. An absorbed dose coefficient would be expressed in gray per becquerel. The radiation weighted equivalent dose coefficient is in sieverts per becquerel, as is the tissue and radiation weighted effective dose coefficient. Finally, even for an acute intake, internal dose is delivered over a chronic period of time, which could potentially extend throughout an individual's lifetime. So we integrate the dose rate over a commitment period to arrive at a committed dose. So next, let's talk about reference individuals. Reference individuals are idealized females and males with anatomical and physiological characteristics defined largely in publication 89. There's a few outside sources of data we need to complete that definition. In this sense, the reference individuals are theoretical constructions designed for the purpose of being used to compute effective dose. Reference individuals do not equal reference phantoms, though phantoms can be designed based on the parameters of the reference individuals. So that's why I've always thought the most appropriate photo to show of the reference individuals isn't a photo of a phantom, it's that of publication 89. So it may not be very exciting, but there you go. This is what the reference individuals look like, a book full of tables and data and parameters. So now let's go back to that last polling question, the one where I'm claiming most of our audience got this wrong, right? So let me explain the answer, why the right answer is the one I gave. So if you're in a country which has adopted the publication 103 system of protection, the coefficients used to determine committed effective dose are those specified by the ICRP with no departure from the anatomical, physiological, and biokinetic characteristics of the reference male and the reference female. Moreover, the effective dose assigned in the worker's record is that value which the reference person would experience owing to the radiation fields and activity intakes encountered by the worker. So the task isn't to compute the dose of Francois or Maria or Derek. Instead, the task is to compute the effective dose to the reference person if it had the same exposure that Francois, Maria, or Derek received. The idea is that if the system is protective of the reference individuals, then it is protective of Francois and Maria and even Derek. So before we hop into the mathematics of the dose coefficient calculation, here's a quick summary of some of the big improvements underlying those internal dose coefficients. They use the improved publication 103 recommendations, notably including the tissue weighting factors. We now use sex-specific reference voxel phantoms for computing energy deposition quantities. The whole body voxel phantoms don't provide everything we need, so we have improved models in the alimentary tract, the gallbladder, and the skeleton. Improved biokinetic models, which you will hear more about later in this webinar. For the first time, inclusion of whole body blood as a source region. And when we have a radionuclide, which is a parent of a decay chain, the progeny in that chain are now always modeled with independent biokinetics. That is, the progeny are now modeled as moving through the body as they should behave, rather than assuming the body treats them identically to their parents. Previously, only select radionuclides were modeled with such independent biokinetics. Finally, we take advantage of the wealth of nuclear decay data in publication 107. Note that these improvements are designed to improve the accuracy of the effective dose, thereby reducing the need for assumptions we had to make previously. All right, so now let's get into the mathematics of the calculation. So we'll start by considering the equivalent dose rate to some target tissue T. So H, capital H is our equivalent dose. The little dot denotes that it's a rate, and we're to some target tissue T. So this is the product of two terms. The first term is what I call the biokinetic or source term, which is the amount of activity in a source region S. And the second term is the energy absorption or physics term, and this is called the S coefficient. And it gives the equivalent dose rate to the target per activity in the source region. To get the total equivalent dose rate to a given target tissue, we simply sum over the contributions from all the source regions which irradiate that target. So if we break down the two terms, if we integrate the activity as a function of time in a given source region over the commitment period tau, so that's this piece right up here, we get the total number of nuclear transformations which took place in the source region during that commitment period. If we divide by the total intake activity, we get the number of transitions in the source region per activity intake. And this is the quantity I believe those in nuclear medicine call a TIAC, a time integrated activity coefficient. Note that the very fancy tilde symbols over the integrated, over the A's here, the idea there is that's just an integration symbol on its side. So the notation there is to remind us that this quantity has been integrated over a commitment period. So turning to the S coefficient, the S coefficient is determined by multiplying multiple terms together. They include the radiation weighting factor, and those are provided in publication 103. The energy and yield of each radiation emitted from a given radionuclide, and the specific absorbed fraction denoted here with a capital Phi. This equation with a summation works well for discrete radiation types such as photon and alpha emissions. For the continuous energy spectrum emitted via beta decay, we need to integrate over that spectrum, but the same quantities are involved. So you notice I didn't bother to define the specific absorbed fraction. Let's do that now. So the specific absorbed fraction, or SAF, is determined by dividing two quantities. The first is the absorbed fraction, which is the fraction of energy emitted from a source region, which is deposited in a target region. So we might consider the fraction of total energy emitted from activity in the liver, which deposits in the brain. That would be our absorbed fraction. And then this absorbed fraction is simply divided by the mass of the target tissue. Sticking with our liver to the brain example, we would divide by the mass of the brain since it's the target tissue. The SAF set used in these latest internal dose coefficients is significantly more expansive than in the past. When you consider the number of source and target region combinations, the 12 reference individuals, and the 4 radiation types, the SAFs alone account for more than 3 million individual data points. What do we need to compute all of the SAFs? Well, we need to define the reference individuals. We talked about that earlier. And this included the need to supplement some of the information in publication 89, such as determining reference blood distributions in the pediatric individuals. We need anatomical models of tissue geometries and compositions, and those fall into 3 general categories. The whole body voxel phantoms in publications 110 and 143. Image-based microstructure models of the skeleton, and mathematically defined stylized models in the GI tract and the lung. Finally, we need to couple the above to a radiation transport engine, such as those shown here. So, and here's an example of what some of those 3 million plus SAFs look like. In this case, we're looking at the SAFs on the y-axis for electrons of varying energy emitted from different source regions within the skeleton. And in this case, what I've plotted is the target being the same for all of these data points. So the target here being the endosteal bone surface. So these are examples of SAFs which came from the image-based skeletal model. All right, so back to our dose coefficient calculation. In the adult, the S coefficients are constant with respect to time. So as our adult ages, nothing changes about the S coefficient. That makes our calculation a little bit simpler. The only quantity requiring integration is the activity, which we went through a little bit earlier. So to get the committed equivalent dose to a target, we just sum the product of the 2 terms over all the source regions. Our reference children, however, are growing after their intake. Therefore, the S coefficient is varying with respect to time. So we need to integrate the product of the activity and the S coefficient over that commitment period. Either way, to get the effective dose coefficient, then we average the equivalent dose coefficients to the female and male and multiply by the tissue weighting factor, which is, of course, the tissue weighting factor is also a sex averaged quantity. And then finally, note that the commitment period here is 50 years for intakes in an adult, but extends through to age 70 for pediatric individuals. And for completeness, here are the tissue weighting factors. Note that the weighting factor, the remainder tissue, is applied to the equivalent dose determined by a simple averaging of the dose to the 13 tissues listed in each sex. There are 4 target tissues which are composed of subregions in our models, and these are those 4. In each case, the dose to the tissue is determined by weighting the dose to each constituent tissue by the fraction shown on the far right. For example, the dose to the colon is determined as 2/5 of the right colon dose, 2/5 of the left colon dose, and 1/5 of the rectosigmoid colon dose. So how do we determine the activity distributions? Very carefully. After all, there's way too much going on this single slide, but hopefully in a couple of minutes you'll understand why I've put so much here. So the biokinetic models fundamentally determine a system of coupled first-order differential equations. Solving that system of equations gives us the activity as a function of time in each source region. So I've shown an example here of 3 sets of biokinetic models which come together and are used for a given inhalation of radioactive material. So on the top left here, we have the respiratory tract model, which you'll hear more about later. On the right is the alimentary tract model. And in the lower left is the systemic biokinetic model. Each box represents a given source region, and each arrow indicates a transfer rate of material from one region to another. So each box gives us an equation like the one that we've shown down here. And this equation has 3 terms. The first represents material flowing into the source region from other regions due to the body's physiology. The second term covers loss of material from this source region due to either physiological removal from that region or radioactive decay, physical decay. And the third term represents ingrowth of the radionuclide we're currently considering due to radioactive decay of its parent taking place in this source region we're looking at. So each box gives us one of these equations, and all the equations depend on one another. Once you apply some boundary conditions, the system of differential equations can be solved to give the time-dependent activities in each region and for each member of a decay chain. So there are a lot of data sets and models which are used to compute internal dose coefficients. Our task group is occasionally asked why this work takes as long as it does. And here's at least one visualization which provides an answer to that question. Each of these ICRP publications listed has provided values or models which are used in computing internal dose coefficients. And this slide doesn't attempt to list the numerous peer-reviewed journal papers, which also provide data sets and models. In short, this is a large effort. If we're to do it with the high quality everyone expects of ICRP dose coefficients, it will take significant time. A few other links, details associated with the calculations are provided on this slide. I'm not going to go through all of them in detail. We make determinations on interpolation and integration techniques necessary to perform the calculation I just took you through. And I wanted to remind you that when we publish an internal dose coefficient, the value includes contributions from all radioactive progeny, which are created after the intake. So to summarize, Task Group 95 provides committed effective dose coefficients for the reference person or representative person at each reference age. These coefficients are specific to radionuclide and chemical form, and they are based on significant improvements in both the biokinetic term and the energy deposition term. So that wraps up the fundamentals of internal dose coefficients. So I will stop sharing and turn the keys back over to Francois.
Thank you very much, Derek. Yes, thank you. As we said before in the introduction, you know that we have a Q&A specific session at the end of the presentation. So I would propose to keep the question for the end of this session or to post them on the chat. We have already one, and you can also post every question you want using this chat. So I propose to switch directly on the second presentation, which is about the rationale for providing the OIR and EIR series. I will try to put on full screen. Here. Okay, so why we start this work many years ago? You all know that ICRP has already provided many publications about the dose coefficient. We had a dose coefficient provided for workers, and this is made by the publication 30 series, which was provided since in the 80s, since 1988. This publication 30 series provide dose coefficient and annual limit of intake for inhalation and ingestion based on the previous reference main data and on previous ICRP recommendation. We then have the ICRP 68 published in 94, which provide updated dose coefficient following the 1991 ICRP recommendation with a new human respiratory tract model, new skeletal data, and revised systemic biokinetic model. We also had the publication 54 and 78 providing guidance on the design of monitoring program and interpretation of result to estimate dose to worker following radionuclide inhalation or ingestion. For the member of the public, we have also the 56 series made of several volumes, which provide age-specific dose coefficient for inhalation and ingestion of 91 elements. And we have for the embryo and fetus and for the nursing infant, 2 publications giving dose coefficient for this specific situation. All these coefficients were compiled in ICRP 119, published in 2011, and I should say that most of these coefficients are still used in many countries, including France. What happens since that is that we, in fact, science have made many progress. We had many change which appear since this period. In physiology and in biokinetic model, we had the appearance of a new reference man. Derek has just given some example and just mentioned it. In fact, we left from reference man and we include the age and specific data in this new reference man. We produce also a new human alimentary tract model, which was produced in 2006. So I will not provide detail on this model, but just few examples of the improvement. In the former model, which was produced in the 30 series, it was a very simple model with 4 compartments describing the behavior of radionuclide in a very simple way. In this new model, what we agree is that after ingestion, we can have a direct deposition on the teeth. We also agree that after ingestion, we can have a direct absorption through the oral mucosa to the blood. We can also have a deposition on the wall of specific organ, and we can also have a secretion of elements. So what you can see from this diagram is that this new alimentary tract model, it's much more realistic compared to the previous one and should be used for those calculations. We have also new element-specific systemic model, which are physiologically realistic. I will not give you an example because there will be 2 of them will be presented by Rich and Vladimir in the coming presentation. We have also a more realistic treatment of the biokinetic of radionuclide daughter. Again, Derek has explained you the main characteristic of this. We'd just like to remind you that when we provide those coefficients for one element, we take into account the biokinetic of the element, we take into account the energy of decay of the element, but we also take into account the biokinetic and the energy of the progeny. And so this is a major improvement that needed to be taken into account. For example, it can be this way of taking account the progeny can be easy to implement, but it can be also difficult for some element. Here I've got the example of radon. As you know, radon is a gas, and it decays into daughter products which are made of particles, which can have different behavior in the body, and this needs to be taken into account when we provide the dose coefficient for the radon gas. We have also new data supporting update of the human respiratory tract model. Again, I will not provide detail because Demetrio, who follow just after me, will give all these details. In dosimetry, we developed a few years ago adult and pediatric reference computational phantom based on the new reference man. Just to remind you that by the past, we used stylized hermaphrodite phantom in the 80s, and now we have the new ICRP family of age and sex-specific computational phantom. And this next slide is just to show you the kind of example of improvement that we have over the years, starting from the stylized phantom in the 80s, and now with the new hybrid and new mesh phantom, which are much more precise, which is really needed, especially for short range internal emitters. We also have new skeletal dosimetry. So just to let you know that the bone is a very complex target organ. It is made of different tissue. And what is the difference between the previous recommendation is that we skip, for the target for the bone cancer, we skip from 10 micrometers layer to 15 micrometers layers. We have also revised nuclear decay data, which was produced in 2008. And I invite you again to download free of charge from the ICRP website. You can download this table, which allow you by just a simple quick click, which allow you to have access to every energy provided by the disintegration of every radioisotope you want to use. We also had change in weighting factors, which was produced in the last ICRP recommendation. Change in the calculation of effective dose. Derek has mentioned that we now have a male and female reference phantom for which we calculate equivalent, from which we calculate equivalent and dose for male and equivalent dose for female. And then we average the equivalent dose to end up with a sex average effective dose at the end. So in monitoring, we also have made progress, thanks to Vladimir, who is there with us, with this concept of dose per content. As you know, this is another way of presenting the way to calculate dose. You can see that it's a very long process, going from the intake to the effective dose and going through the transformation in tissue, calculation of emitted energy, and so on. And this, in this diagram, it shows you that when you do not know the intake, you can start directly from the bioassay content, go back to the intake using retention function, and then using the dose coefficient, calculating effective dose. And in this, with Vladimir, they produce a new concept, which is a dose per content, which allow you to calculate directly the effective dose from the bioassay, and which avoid any risk of mistake. So all this progress, this new data, this new recommendation, definitely support a revision of the previous dose coefficient, the previous dose report, and support the provision of new dose coefficient with guidance on monitoring program and data interpretation. This was done For external dosimetry, in external dosimetry, we have produced new dose coefficient in 2010, and that should be completed for internal dosimetry. So the work has been divided in two parts. We first focus on the revision of models and dose coefficient for the worker. So that was published under the OIR series. Again, it's occupational intake of radionuclides series. And the second part is about the revision of model and dose coefficient for members of the public, including the embryo and fetus, and including the transfer via the milk. So where we are now, for the OIR series for the worker, we have ICRP has already published 5 publications from 2015 to 2022, with ICRP number ranging from 130 to 151. In this OIR series, we provide a review of available data on inhalation, ingestion, and systemic behavior of radionuclides. We also provide the biokinetic model and biokinetic data. We provide advice on monitoring techniques and detection limit for every element. We provide the coefficient and bioassay function for about 1,200 isotopes, which are actually the isotopes which are provided in the ICRP 107. We provide this coefficient for different chemical forms, which are the main chemical forms which are found at the workplace. We provide the dose coefficient for different particle size, for gas, for vapor, but also for particle size ranging from 1 nanometer to 20 micrometers. We provide also dose coefficient for exposure by submersion for some noble gas. And all of this is available using an data viewer, which can be downloaded by in ICRP website, and on which you will have a demo at the end of this presentation. So how did we split the work in different parts? OIR part 1 was about the methods. Part 2, part 3, part 4, and part 5 were about specific element. In part 2 and 3, we have the most important element for radiological protection. In part 4, we had the lanthanide and transuranic elements. And in part 5, which was published, which was just republished a few years ago, we had every other element. For the member of the public, the philosophy is exactly the same. The EIR series for environmental intake of radionuclides will replace the 66 series. It will be dedicated to members of the public of different age, including the young age and the adult. It will also use physiological data specific to the public. As you know, for the public, the reference grazing rate, for example, is different from the worker. We will also use specific physiological data according to the age. We have different tissue mass, we have different transfer rate, and so on. And so the content of this series, we will have, as for the worker, a specific review of data on inhalation, ingestion, and systemic behavior of element. We will have provide age-dependent biokinetic model and data. We will not provide data for bioassay because we do not expect that the member of the public will be asked to provide any bioassay for measurement. We will provide the dose coefficient for the same isotope that are treated in the OIR series. We will also provide this coefficient for different chemical forms, those which are found in the workplace, plus those which can be found in the environment. We expect that after an accidental release of the element in the environment, they will form specific chemical form with specific binding to the food component, for example. We will provide this data for particle size ranging from 1 nanometer to 20 micrometers, as for the worker. And again, as for the worker, all this data will be available using the data viewer. So the schedule is as follows. In part one, we have, which is already in press, we have the element which has the most important for radiological protection. It is in press and it is expected to be released within few months. Part two and three will contain data for every other element. We expect to have the first draft of part two ready for the end of this year, so in few days from now, and this part three in 2025. And then we will finish the series with the embryo, fetus, and the nursing infant from 2026 to 2027. So I finish now. I propose to give the floor to Demetrio, who will explain you and show you the main characteristic and the new data that we use in the human respiratory tract model. Thank you, Demetrio.
Okay, thanks, Francois. So I hope I don't have the problems I had before in sharing the screen. And there. Please let me know if you can see it.
Can see it. Do you want to try moving forward?
Yes. I'm afraid Zoom tries continuously close, so I'm afraid that maybe it is better.
It moved for me.
It moved. Okay, but okay, I will probably have to close a window which opens continuously, asking me to close. But let's see, we can try this way. So apologies for this. So the ICRP human respiratory tract model has been published and is described in full in ICRP 66. The model has been used since to calculate inhalation dose coefficients for both workers and members of the public. It has now been updated in ICRP 130, which is the first part of the series on occupational intakes of radionuclides. The revision is to take account of new information which has accumulated since its publication in 1994. Although I think the main features of the model are still are unchanged. So the model, the revised model, has been used already in the OIR series and is being used now for members of the public in the EIR series. There. So the HRTM is a quantitative model. It's used to calculate activity in the respiratory tract regions as a function of time, and is used to calculate doses to the target tissues. It is applied to inhalation of aerosols, which, as explained, with particle sizes, in this case, up to 20 micrometers, for inhalation of gases and vapors. And it applies to all members of the population and for adult worker in the OIR and for reference individual for each of the 6 age groups for the members of the public. For those who are not very familiar with the model, this is how it is represented. And there are essentially 5 main regions, 2 extrathoracic regions, simply the nose and the throat, the bronchial region, which includes the trachea and the bronchi, the bronchular and the alveolar interstitial. There are lymph nodes associated to the extrathoracic airways and to the lungs also included. So the model essentially is used to calculate the deposition in the regions after an inhalation and to describe the removal of the particles due to some clearance mechanisms. And it is the clearance part of the model which has been subject to the main revisions, and this is the main topic of the talk. I start anyway with the deposition. So the deposition model of the ICRP 66 has not changed. So we calculate the deposition, the total deposition and the regional deposition in the same way. There is only a minor change in the partitioning of the total deposit in the extrathoracic regions. So the deposition model depends on some parameters, anatomical and physiological, which are age-dependent, and on parameters which define the inhaled aerosol, like particle size distribution. Default values for the particle sizes defined as the activity median aerodynamic diameter are the same as before. It's 5 micrometers for the workers and 1 micrometer for the members of the public. The only exception to these default values are for the inhalation of aerosols of the short-lived progeny of radon, short-lived nuclides of polonium, lead, and bismuth. And this is described in part 3 of the OIR. So the clearance mechanisms, there are mainly 2 main pathways. One to describe the movement of the material from the respiratory tract into the alimentary tract and the lymph nodes, which is called particle transport, and transfer into blood, which is called absorption into blood. So these 2 mechanisms are assumed to be independent of age and sex. This is important simplification, relevant. The particle transport is assumed to be the same for all. Instead, is assumed to be the same in all regions of the lungs, except in the nasal passages where there is assumed to be no absorption. These 2 mechanisms are described, are modeled with so-called compartmental model that Tarek was explaining in the first talk, and also with constant transfer rates. So we can start with the revision of the particle transport model. You can see on the right, you have the revised model, which is simpler, has less compartments. The reference values for the transfer rates are derived as much as possible from human studies. And in this case, more precisely, we have analysis of human volunteer data for the derivation of the parameters in the ET1, ET2, the bronchial and the bronchial region, while for the rates in the alveolar region, responsible for the very long-term retention in the lungs, these parameters has been derived mainly from the study, the analysis of data from 2 accidental exposures to workers, to 2 groups of workers. Going a little bit in detail, the changes in the different regions, starting with the extrathoracic region. I said there are no major changes in we calculated the position, so the total deposit in the extrathoracic region is the same as before. It still depends mainly on the particle size of the inhaled aerosol. There is a change in the particle transport. You can see now that there is about 2/3 of the material which is deposited in the nasal passage, in the ET1 compartment, is cleared to the ET2 region. This means that now about 80% of the deposit in the extrathoracic region is available to be absorbed into blood in the ET2 region, while we know that there is no absorption in the ET1 region. And this can lead to increase in dose coefficients for only for very soluble materials, just because the material, there is a very strong particle transport rate in the ET2 region, which competes with the absorption into blood. Due to this increased amount of material which transits through ET2, there is going to be also more activity excreted in feces compared to the old model. Moving to the bronchial tree, the main change is that there is no slow clearance anymore in the bronchial region, but still in the bronchial region, which clears with a half time of about 4 days now. And the consequences of this is that there could be decreased in lung doses, more evident for alpha emitters with sufficiently long radioactive life, and more for moderately soluble materials. There are probably no significant changes if the material is very soluble, as this would be anyway the dominant mechanism, clearance mechanism in both the old and the new model. Going to the alveolar interstitial region, the evidence here showed that the HRTM, the original HRTM, was underestimating the long-term retention in the lungs. And so the new model addresses this point. And the new structure on the right, where you have only two compartments, one for the alveoli and the interstitium. So this structure has been published and used for the analysis of autopsy data of US coal miners. So we have adapted the structure, the new structure, and estimated the parameter values on the biokinetic data for the two accidental exposures to groups of workers. First group of 7 workers exposed to cobalt-60 insoluble material, and the second group of 6 workers exposed to plutonium dioxide, so 2 different materials. First group follow up for 15 years, and the second for more than 30 years. So on the right, you can see now the new parameter values. About 2/3 are cleared to the bronchial region, but 1/3 is cleared into the interstitium, where it practically is sequestered almost indefinitely, as it clears very slowly to the lymph nodes, so with a half-time of about 60 years. This 1/3 fraction is very consistent also with the result of the analysis on the coal miners done independently. So this higher retention, if you compare it with the old model, where only about 10% was retained for about 20 years, is strictly speaking applicable only to very insoluble material, which means that it is the absorption, the solubility of the material, which is going to be the limiting factor for the retention in the interstitium. In fact, for typical insoluble materials, the increase in lung doses are about 50–100% for long-lived alpha emitters. It has little, this change in the transport rate has little effect on more soluble forms. So moving to the absorption, which is the second clearance mechanism, competing with the particle transport. We already said that absorption applies to all regions except the nasal passages. It is treated as a 2-stage process. So you have first the dissolution of the deposited material, and then the uptake of the dissociated material or radionuclide. So it's a time-dependent process. A simple way to represent it is with this simple compartmental model on the right. In most cases, 2 compartments are sufficient, where you have a fraction which dissolves rapidly, and the remaining dissolves slowly at the rate SS. And then the uptake is considered practically to be instantaneous, or at least much faster than the dissolution. On the other hand, there are some elements for which this the uptake is slower, and this is can be modeled by adding an extra compartment for this bound state material, and so this compartment collects a fraction of what the dissolved material, and then this goes into blood with a rate, finite rate SP. The important thing here is that the bound material is assumed to be located in the epithelium, and so not to be subject to particle transport, which means that you can have a significant increase in the lung dose if the rate SB is very slow, just because there is no other removal mechanism for this bound material. So in the revised model, the compartmental, the structure of the compartment is not changed, it's the same, but we have revised the values of the parameters of the absorption model. So there has been a review of the experimental data to derive the absorption characteristics of this material, all possible materials which are relevant to radiological protection. And then this large data set of estimated parameter values have been used to select 3 sets of parameter values, reference parameter values, which could be used as representative of materials which we would classify as soluble, moderately soluble, and poorly soluble, or in ICRP terminology, absorption types F, M, and S for fast, moderate, and slow. So if for a given material there is poor information about its absorption characteristic, these are classified and put in one of these 3 default categories. Where we had sufficient information, we were able to propose material-specific values, not it's just for a limited set of materials, and element-specific values for bound state parameters and for the rapid absorption rate for soluble materials. Here there's a comparison of the default values in the original model and in the revised model. There is essentially a reduction of the rapid dissolution rate from 100 per day to 30 for the fast and 3 for the moderate and slow types, and an increase of the rapidly dissolved fraction for the type M and S. There is no bound state included in any of the default types. It wasn't in the old model, and it's not in the new. One comment is that these changes to the default values can have as an effect that there is a reduction of the rapid absorption in the extrathoracic airways and in the increase of the rapid absorption in the lungs. Regarding the position, gases and vapors, also here the revised model has simplified the approach. Before there was a classification according to the solubility and the reactivity of the gases, which has not been found to be particularly helpful and is not longer used. There is now only a single class, so the default values, gases are assumed to deposit 100% in the respiratory tract and to be absorbed as a type F material. In the table, you can see the partitioning between the different regions, and just 3 examples of cases where there was enough information to be able to specify material-specific values for, in this case, for tritiated water, elemental iodine, and mercury vapor. We have kept also a special absorption time, which was in the ICP 66, which is a type V, very fast to be applied to gas or vapors. And to conclude, just to say, remind again that the description of the revised model is in both part 1 of both the OIR and the EIR publications. And the absorption parameter values are for specific materials or elements you are interested in, can be found in the corresponding element chapter in the following EIR or OIR parts. Okay, thank you very much.
Thank you very much, Demetrio. Before we switch to Vladimir, I've been told that it will be easier for everybody to ask the question directly using the chat. So we will try to answer at the end of the session rather than discussing using the microphone. So please, everybody, use the chat to ask your question. Thank you. Vladimir, you have the floor for the iodine.
Thank you, Francois. Hello, everybody. Today's subject, iodine and its biokinetic model. Can you see my slides?
Yeah, we see them.
So iodine is a trace element that is naturally occurring in the environment and in some foods. And it's volatile halogen, which occur mainly in oxidation states 1, 0, and 5. And most common chemical form of iodine solution is iodide, and iodate. Our body needs iodine for normal functioning, for synthesis of thyroid hormones, and hormones control body metabolism and many other important functions. In industries and medicine, iodine may be encountered in varied chemical forms like organic compounds, vapors, gases, particulated forms. And iodine, actually, most of iodine, which usually we didn't occur in nuclear reactors. It's decay product of fission fragments. Some of isotopes, or 24 isotopes of iodine, are not fission products, can be produced by, for example, accelerators. And iodine is widely used in medicine. Iodine 123, 125, 131 is medical isotopes, and simultaneously iodine 131 is major troublemakers during emergency and actually normal operation of nuclear facilities. Here, iodine also gets largely produced in nuclear reactors, but because of their short-lived, they not really get major concern for radiation protection. I have to say that, for example, iodine in Chernobyl accident caused a number of problems, and this is example of comparison of what we done during Chernobyl and during Fukushima accidents, and it's rather unique numbers. A little bit less than 500,000 direct measurement of thyroid gland, iodine in thyroid gland during the first weeks of the emergency. And absorbed doses to thyroid gland in Chernobyl case was really large. Some of doses well above 5 gray, and definitely it's caused a number of problems. At this moment, it's probably a unique cause of really statistically observed and clinically observed cancers. As we have at this moment more than 18,000 thyroid cancer. Fortunately, most of these cases are really curable, and number of deaths is really limited. And so before we switch to real modeling, let's speak about real life, how it's how it's behavior in the environment and human body. As I said, it's enter body, stable iodine enter body with food, and after ingestion, usually readily available for absorption by thyroid gland. WHO recommend daily intake of stable iodine for adults 150 milligram and at least 200 milligram during pregnancy and lactation. And later we talk about this. And extensive survey data on dietary and urinary iodine excretion indicates that there are plenty of regions with sufficient iodine supply, but there are a number of places and countries where there is substantial iodine deficiency. In Japan specifically, it's rather peculiar, and because of consumption of seafood, if it's really traditional diet, it's depend on particular person. The iodine intake will be much higher. It will be thousands of milligray a day. And typically, women has lower daily consumption, up to 30–40%. Thyroid gland, which actually accumulate iodine, is one of the earliest endocrine glandular structure, and appear as a day 16 of gestation. And on the 5th gestation week, we usually can detect the thyroglobulin as which already generated, and by week 11, thyroid gland usually fully functioning. Actually, it's reflected in our models. Thyroid itself located at the neck and consists of the granule parenchyma of the thyroid consists of spherical follicles of various sizes, from 50 to 500 micrometers typically, and the number of such follicular structures will exceed 20 millions. And follicle contains unique compound thyroglobulin. And here you can see it's this thyroglobulin as a component of the follicle, and masses of thyroid glands really variable. For males and females, you can see these features, and there is a substantial variation for among individuals and among different populations. Thyroglobulin and it's actually the material which accumulate and help produce thyroid hormones. Major thyroid hormones is T3 and T4, which is produced by synthesis in thyroid gland. The thyroid hormones increase oxygen consumption, metabolic rate of most body tissues, and it's essential for growth, maturation, mental activity. The level of thyroid hormones in the systemic circulation should be maintained at a specific fixed level, and deviation usually associated with severe health problems or such status like pregnancy, which also could be treated as a very special health condition. And iodine, it's thyroid hormones mostly consist of iodine. It's 65% of T4 and 58% of T3, which primarily derive from our diet. You can see this microstates actual photos. Follicles is surrounded by follicular cells, which actually produce the thyroid hormones, and this is ultrafine structure with the scale 2 microns with nucleus of follicular cells. Have a look actually how it's ongoing. It's a complex process, and just to general feeling what is it situation is you can see this the element of follicular and one cell which produce help to produce thyroid hormones with special transport mechanism. Iodine pumped to the cell and secreted to the follicle content. Simultaneously, the cell produce thyroglobulin, which also by exocytosis secreted to the globulin. And synthesis of by iodination, thyroglobulin obtain iodine, which consecutively endocytosed by the cell and secreted to the bloodstream. This is some thyroid hormones, and major thyroid hormones is thyroxine, T4, which contains 4 iodine atoms, and based on the tyrosine, actually is the basis for all hormones. The iodination of T4 can produce T3 or reverse T3. Let's see later. Important that this synthesis and deiodination process of thyroid hormones heavily controlled by the hypothalamus and pituitary gland, which produce respective hormones and regulate positively the hormone secretion, and secreted hormones T3, T4, which produce reverse feedback to the respective glands. So it's really a complex mechanism, apart the internal self-regulatory mechanism of the cells producing thyroid hormones. Thyroid hormones deiodination occur mostly in the body tissues, in remote body tissues, and it's important to understand that there are a number of enzymes which actually doing this, and deiodination by the outer ring can produce the most active thyroid hormones 3,4, and deiodination of the inner ring can produce inactive form of thyroid hormones. Actually, it's the way of deactivate circulating thyroid hormones and produce the metabolites which not biologically active. And just for your general picture, this is enzymes, list of enzymes, 3 enzymes, D1, D2, D3, and their expression in different tissues. So it's really rather complex mechanism, which finally regulate a number of processes in our body. So about modeling. Those of you, and many of you, really have long-term experience in this area. I'm pretty sure you're familiar with this model. Rick's models, rather classical, it's famous 3-compartmental model. It's probably one of the first really recycling and physiologically oriented model. Yeah, you already heard that this is first-order kinetic differential equations. It's just system of differential equations. It's more or less straightforward. For this particular model, it can easily be handled by hand without computers. And it's a rather useful model, honestly speaking, especially if you're speaking about iodine 131. One of the substantial disadvantages of this model is intentionally actually ignore fast processes because of the structure of the model, the simplicity. Model itself was calibrated for iodine 131 on clinical data, and really applicable for such data. It's produced relatively acceptable results, but again, as I said, it's not about the first hours, and some long processes also are not here. Such model rather difficult to adjust for specific needs, like if you have non-reference kinetic and non-reference individual. You may have it. Derek already indicated you that for normal conditions, it's okay. You have to apply the ICRP system and regulatory approach that you actually demonstrating of compliance. But in case if an emergency, you may need some more, you may need some additional data, you may wish additional more specific assessments. And one of example of another specific needs, it's the dosimetry of embryo and fetus and dosimetry of newborn breastfed child. This model was developed already 20 years ago. And originally, my intention was to use Chernobyl data for this model, because during Chernobyl we had a number of in utero exposed individuals and breastfed individuals. And honestly speaking, it was really a problem because, you know, during early stage, mother asking you whether she have to terminate pregnancy, what will the dose, what will the consequences. And those times we have no such approach, no such information, no data. So it was more or less urgent. Model developed actually 15 years after Chernobyl. And in reality, Chernobyl data appear not really appropriate for proper development. We end up with use of clinical data. Again, nowadays it's rather unique data sets, because plenty of such clinical data obtained probably not in the best ethical way. Nevertheless, model contain new structures like gastrointestinal elements, salivary glands, and gastric secretory cells, which in early hours after intake may contain substantial portion of iodine. And it's also rather symmetrical structure for in utero. Model more or less adequately reproduced kinetic and doses for short-lived iodines. And new model, which actually Rich present here, developed already practically 15 years ago. It's also physiological oriented model, which includes more new compartments and capable to project conditions and use applicable for conditions far away from the reference. Some result of this model is short-term kinetics, which actually in clinical applications, 2 hours uptake, steroid uptakes. It's just standard clinical test for steroid. And old model, RIX model, cannot reproduce properly these kinetics. And this RICH model, new ICRP oil model, is actually properly reproduced and applicable for short-term kinetics. Another story with non-reference intake of iodine, stable iodine, and in reality is if you have a low intake of iodine, steroid uptake could be really high. You can see it's really up to 90%. It's observable data, and some data which clinical data which were used for this model. It's a number of publications, and you see this really depends the intake, iodine intake and steroid uptake will be really high or really low. And also important data is rate of secretion of hormonal iodine in different individuals. This is kinetics of a new model, exchange rates. Have a look on specific values. This value actually depends on the ratio of iodine intake, dietary intake, and iodine secretion, which this parameter can be modified. And another important parameter to look, this value, which actually somehow effective character time, or you could calculate as a effective biological half-life of the iodine in steroid, it's actually hundreds of days. And this is important if you look on the kinetics of iodine 131, you will realize that iodine 131 decay, physical decay, really dominating. So it's really one of the most factors rather than biokinetic itself. A model will include also compartments for iodide in the systemic circulations, a number of compartments. Compartments for iodine in steroid, which we discussed just previously, behavior of iodine in steroid, and also extrasteroidal organic iodine in number of compartments. Let's have a look on model predictions. And as I said, in case of iodine 131, because of physical decay, this course really has a substantial slope. It's substantially physical decay rather than biokinetics. You cannot say this about urine excretion. This is rather unusual behavior for radionuclides in human body. You can see this some secondary peak of the behavior because of recycling of iodine in the human body. And for iodine 129, which is really extremely long term, it's much more pronounced. And probably some final slides to demonstrate importance of proper physiologically oriented models and modeling of short-term kinetics. And you can see that, for example, for short-lived iodines, like 1,3, 2, and other radionuclides, it's really ratio between the previous predictions and current predictions of the doses really substantial. So this is current stage. It will be some extension of this model in the age-dependent series. And we are looking forward for the new series, new documents, which we are now working, is about emergency dosimetry, which will include some additional non-reference dose coefficient for emergency conditions, non-reference individuals, and some early application of this new model already gets done. For example, ANSCARE. One of you actually asked in questions, online questions, whether it's Fukushima accidents. For Fukushima accidents, we applied something new as a dose coefficient. Yes, for example, ANSCARE, United Nations Committee on Effect of Atomic Radiation, in its recent report on Fukushima 2021 report, use this new model to project doses for individuals in Japan who consume substantial dietary intake during the accident. So yeah, it's already practically applied. Probably that's all. Thank you very much for your attention.
Thank you very much, Vladimir. I propose to switch directly on the model for the cesium. Rich, you've got the floor.
Okay, thank you, Francois. I will try to share. This looks like it. Can you see that?
Yes.
Okay. I'll describe the ICRP's current biokinetic model for cesium and give some historical background on the model. Cesium is an alkali metal that follows the essential alkali metal potassium in the body. The ICRP's current model for systemic cesium is based on a modeling scheme originally applied to potassium. By the current model, I mean the OIR model. The potassium model was built around a blood flow model with parameter values based on blood flow rates, tissue-specific rates of extraction from blood, and a steady state distribution of potassium. The same approach was applied to the alkali metal rubidium a couple of years later, and rubidium is a very close analog, both chemical and physiological, of potassium. And the model was much later, 15 years later, applied to cesium. And modified versions of these three models, the models for potassium, rubidium, and cesium, were adopted for use in the ICRP's OIR and EIR series, where the EIR series model is age-specific. Rubidium and cesium were discovered in the 1860s by Bunsen and Kirchhoff, where Bunsen is the Bunsen burner guy. And in the 1880s, Sidney Ringer tested whether rubidium or cesium could substitute for potassium in maintaining beats of the isolated frog heart. And he found that rubidium substituted very well for potassium over as many hours as he cared to observe it. Cesium also maintained heartbeats, but changed the rhythm of the heartbeats and worked for at most 20 minutes. And over the years, these three elements, potassium, rubidium, and cesium, have been used extensively for physiological studies of the ionic channels and discrimination between chemically similar elements. Rubidium and cesium have been found to compete with potassium for transport in all the studied potassium transport systems, including active transport into cells via the sodium pump and passive transport out of cells along concentration gradients. The discrimination between among the three elements differs somewhat with the pathway, but as typical values, potassium is chosen over rubidium by about a 4:3 ratio, and potassium is chosen over cesium by a much larger ratio, at least 5:1. For example, if cesium and potassium atoms are circulating in blood, the extraction fraction, or K, when passing through a tissue in blood, is on the order of 5 times as high as the extraction fraction for cesium. In the 1950s, the emergence of tissue of fission-produced cesium-137 led to a much wider group of studies of cesium biokinetics, more at the whole body level than before. And on the left, we see data for individual subjects, and you can see that the removal half-time from the body increases with age from less than 20 days in pre-adults to about 2 to 4 months in adults. And on the right side, this shows mean long-term half-times of cesium for male and female subjects in 8 different studies. And the largest study had 239 people, the smallest about, I forget how many, 7 or 8 people. And you see that in every study, the mean half-time for males was about 15 to 30% greater than that in females. The figure on the left, the only figure, I guess, shows the ICRP's previous systemic model for cesium, used from about 1982 until the OIR Part 3 was published in 2017. And cesium in that model is assumed to be uniformly distributed in tissues, but there's assumed to be 2 phases of retention. 10% is removed with a half-time of about 2 days and 90% with a half-time of about 110 days. And the same type of a simple model was applied to potassium and rubidium during the same time period. The potassium retention half-time in adults in the model is assumed to be 30 days. The rubidium half-time is assumed to be 44 days. Potassium and rubidium move much faster in the body and are excreted much faster than cesium. Okay. Now the current, meaning the OIR ICRP model for systemic cesium, is based mainly on 3 types of information, the same types that were originally applied in the potassium model. It's based on a blood flow model, tissue-specific extraction fractions, and the equilibrium distribution of stable cesium. And this shows the original version of the blood flow model that underlies the OIR models for cesium, rubidium, and potassium. And in the OIR document, we didn't look in this detail at the blood flow. There's some grouping of tissues into other tissue, and accounting for the greater amount of blood flow that would go to other in that case. But this was originally developed as a dynamic blood flow model, and it was designed, it it could be applied to, in effect, track the sites of decay of a very short-lived radionuclide used in nuclear medicine, like rubidium-82, which has a half-life of 75 seconds. But it hasn't been applied very much as a dynamic blood flow model. It's just mainly it's assumed that the blood is a uniformly mixed pool. It's assumed that in the case of the OIR and EIR models. Another input into the models is the reference equilibrium distributions of potassium, rubidium, or cesium, whichever you're dealing with, in the body. And here's some examples for the reference adult male for selected tissues. And of note is the fact that most of the body's potassium in the adult male is contained, potassium, rubidium, or cesium in the adult male is contained in skeletal muscle. About 2/3 of it in the case of potassium and rubidium, and about 80% as reference values for cesium. And here are some examples of extraction fractions for cesium, which go into the model also. The highest extraction fraction is found for kidneys, and it's about 0.2 for cesium, compared with about 0.9 for potassium. And the lowest extraction fraction among tissues is for brain. It's only like 0.2% extraction for cesium, compared with about 1.5% for potassium. 0.2 for cesium, 1.5% for potassium. And here's an example of derivation of the transfer coefficients using the blood flow model. This is a transfer coefficient from blood plasma to tissues in an adult male for cesium. The transfer coefficient, in simplistic terms, just tells you how fast that the element is being taken up, being transferred from one tissue to another, or one region to another. And in this case, it's the product of the extraction fraction. 0.1 is the extraction fraction assigned to skeletal muscle for cesium, times the fraction of cardiac output assumed to go to skeletal muscle in the reference adult male, times the cardiac output in the reference adult male. And the product of these three values is 30 per day. Continuing this example to illustrate the derivation of transfer coefficient from the tissue, from skeletal muscle back to blood plasma. This is calculated from the equilibrium equation, assuming chronic intake, when the body comes into equilibrium, the transfer coefficient out, meaning a transfer coefficient from skeletal muscle back to plasma, times the fraction of total body cesium in skeletal muscle at equilibrium equals that the left side represents outflow from muscle to plasma. The right side represents equal flow at equilibrium from plasma to skeletal muscle. And on the right side, that's the transfer coefficient from blood plasma to times the fraction of total body cesium assumed to be in plasma. So we know TCN from the previous slide, that's 30.02. So we can solve for TC out as shown on the bottom. And that's 0.0751. Way too many significant digits. But that indicates that the half-time of removal of cesium from blood plasma or from muscle, that would be about 9 days based on that rate. So that, but if you're on the outside of the body measuring the half-time of cesium in the body, it's closer to 100 days for an adult male. What's happening is that half-time from muscle, the effective half-time is much longer because of recycling, constant recycling between blood and muscle. And okay, here there's more to the model for cesium than just the blood flow model part. There's some parts of kinetics of cesium that cannot be described in terms of the blood flow model. For example, the exchange of cesium between blood and the red blood cells, RBC. That can't be described. The amount going to RBC cannot be described in terms of cardiac output. And on the bottom, these are excretion pathways. The amount lost in sweat, urine, or feces has to be estimated by other means. It doesn't fit into the blood flow modeling pattern. And on the right, there's a great deal of exchange of cesium between the systemic tissues and circulation and the GI tract contents. We know there's a lot because the way that cesium is chelated in emergency situations is by feeding the patient Prussian blue, which attaches to the cesium that's contained in the GI tract contents and carries it out in feces. And we know that it's very effective over several days as a chelate. Now, this structure doesn't look like the structures of all the other models in the OIR series. So we restructured the model as shown here to have a central blood compartment. The transfer coefficients, almost all the transfer coefficients could be carried over without change. And the model was, and this was designed so that the predictions of the model shown in the previous slide were changed hardly at all. The time-dependent activities in tissues, that is, for cesium isotopes. And here are model predictions for cesium retention in adult males, compared with observations for 14 adult males from 3 studies. There were a total of 14 adult male subjects. And it fits reasonably well. The model predictions fit reasonably well. And that's total body retention. There's not a lot of information, not a lot of direct information on the early distribution of cesium in humans, but there is a lot of information from different animal types, including rodents and pigs and dogs and other animals. And you can't expect these to be numerically identical because for potassium or cesium kinetics in rats is not identical numerically to cesium kinetics in people, but the patterns are very much alike. As you can see, the kidneys has by far the highest concentration at early times, and the rat studies here were the rats were measured over the first 4 days after intake, and the model predictions for humans, adult humans, are shown over the same time period. So the kidneys have the highest concentration, followed by heart, then liver, then skin and muscle start out very much alike, but gradually muscle becomes the tissue with the highest concentration of cesium. And brain starts out very slowly because it has a very low extraction fraction of cesium from blood, but it has a long retention time, so the content keeps growing over time. For the rat studies here, there were about a dozen other tissues considered, but I just showed enough here. I didn't want to clutter it with too many curves. Okay, this shows the model predictions for adult humans for a longer time period, 30 days, and you see that after several days, the concentration of cesium in muscle is quite a bit greater than the concentration in the other tissues. The second is still kidneys. The second highest is kidneys because of the high blood flow and high extraction fraction for kidneys. Liver comes in pretty close because of a high blood flow, which includes not only arterial flow, but a great deal of even more blood flow from the portal vein coming through. So it's hard to this same pattern is seen for laboratory animals, but for other animals that have been studied most, the retention time of cesium in the body is not nearly as high as it is for humans. So the curves fall off very fast for other animals, for the most studied animal species. And this slide shows it compares dose coefficients for selected cesium isotopes based on the OIR model with values based on the previous two-compartment model that I showed you earlier that was used for many years by the ICRP. And you see for short-lived radionuclides, which are the two on the left, short-lived cesium isotopes, you see quite a lot of difference. You see, like, for example, the kidneys for cesium-130. The kidneys based on this OIR model, the dose is 25 times higher than the dose based on the older model. But for the two most important cesium isotopes, cesium-137 and cesium-134, you see more modest changes from the old model. The difference for the short-lived radionuclides, what's happening is the distribution of concentrations among different tissues is very high, as you saw in the earlier slides. But the differences decrease over time. Differences in the distribution of cesium in the body is still higher in muscle than in most other tissues, but muscle is fairly uniformly distributed in the body. So we don't get great differences in dose estimates for cesium-134 and cesium-137 because in the old model, uniform distribution in tissues was assumed. In the new model, it's not too far from uniform distribution. The main difference being that the concentration in muscle is much higher than in other tissues. So, in summary, the current model for cesium is based largely on a blood flow model, cesium extraction fractions, and equilibrium distribution of cesium, although there are several add-ons to the flow model to fill out the entire model. The model is most strongly supported for adult males because there's a lot more information for adult males than for other segments of the population, especially on the distribution of stable cesium in the body. But the empirical data for cesium are sufficient to check the theoretical approach for both sexes and all ages. And thank you for your attention.
Thank you very much, Rich. We are a little bit late on the schedule, but anyway, it's nice and it's time for us to switch on the presentation from Tracy, who will expose you and present you the difference between the old new dose coefficient and the new one. Tracy? We can see your slide, but it's not the first one.
You're also muted, Tracy.
Thank you. Hello, everybody. And I must admit, when I was asked to present this, I thought, where on earth do I begin? As you will have heard from the previous talks, there is such a plethora of changes. It's quite daunting to kind of think, where do I dive into this? So what I've decided to do, although this has covered the OIR as well, I've focused more on the dose coefficients for EIR here. But what I'm going to do is talk through the different changes. You've already heard some of the changes from the other presenters, but what I want to do is compare the actual values with the previous methods of doing it, just to draw out the differences that we've had to take into account with this series of dose coefficients. So it's very slow to respond. Okay, so Derek talked you through the calculation of effective dose, and fundamentally for EIR and OIR, it's the same, except that we are now sex averaging the doses. Previously, sex averaging was implicit in the use of the hermaphrodite phantoms, and now it's explicit in the use of the sex-specific phantoms. There have been changes to WT. We've already encountered those, but here I've actually put in the old values as well. And look, in the end column here, we've got the ratio of the new to the old values. So you can see that for breast and remainder, there are quite substantial increases in the WT, whereas the values are lower for gonads and for urinary bladder, esophagus, liver, and thyroid. Sorry, got the wrong one there. Remainder and gonads. No, breast and remainder are higher. That one is lower. I'll get there in the end, but you've got this to refer to. Okay, moving on. So the tissues that constitute the remainder dose have also changed. There are some similarities. The ones in black are carried over. The red indicate ICRP 103 additions. So we've included now gallbladder, heart, lymphatic nodes, oral mucosa, and the prostate for the male. Brain was included in this list in the ICRP 60 calculations, but it's now been bumped up and has got its own explicit WT. And as Derek said, the calculation now for 103, under the 103 scheme, is a straight average of these 13 doses for the male or female. Obviously, for male, you've got prostate, for female, you've got the uterus. And that's quite a departure from the old remainder dose calculation. In ICRP 60, they implemented the split remainder rule. So in those cases, if an equivalent dose of one of the remainder tissues or organs received an equivalent dose which was higher than any of the other equivalent doses which had a specific weighting factor, then it would be given half of the weighting factor, and the other half of the weighting factor would be applied to the average, the remaining remainder doses, tissues. But the contributions in that case were mass weighted, whereas now it's a straight arithmetic average. So that can make some differences because the remainder WT has increased quite a bit this time as well. This has already been shown, but it's worth reiterating here. So this is the human alimentary tract model. And again, you can see there's scope for a lot of changes here, especially if any of these other compartments are invoked for a particular radionuclide or element. Demetrio covered the HRTM in quite a lot of detail and talked about the changes to the parameters, the structure and absorption. So I'm not going to cover that again here because he did a really good job on that already. Okay, moving on to SAFs, which again Derek's touched on. But what I want to draw out here is the changes between the old system and the new. So starting with alphas, under the ICRP 60 scheme, there was limited energy dependence, and that was generally for the HRTM only. And the rest, and for everything else, there were 3 categories of SAF. There was self-dose, so complete absorption across all energies. A walled organ, in which case we had to use the ICRP 30 expression, give the reference here. Or if it was, say, tritium, where you were looking at whole body source and all targets got the same SAF, and that would be equal to 1 over the whole body mass. Okay, moving on to betas, again, under ICRP 60, again, limited energy dependence. Energy dependence was adopted sort of piecemeal throughout the publications because it was a time of quite a lot of transition in the way we were developing models and moving forward. So we had, for example, energy dependence for the bone surface, for the HRTM, and also for the human alimentary tract model when that came in. Otherwise, the categories were the same as for alphas. And for photons, we had energy-dependent SAFs, but they were based on the merged geometric phantoms. Additionally, now we have got inclusion of neutron SAF values with nuclide-specific WR values for these nuclides given here. And this data is all available within the SAF data sets, which are freely available on the ICRP website as supplemental data under the relevant publications. Okay, so again, going back to the HRTM, Demetrio talked about some of the structural changes within the actual model, and some of these required changes then in dosimetric assumptions regarding the bronchial and bronchiolar regions. So that necessitated some recalculation of SAFs within the lung for use in OIR and EIR. Publication 66 electron SAFs were augmented as well with selected values from the reference computational phantoms in cases where absorbed fractions had previously been assumed to be either unity or 0. So it was kind of completing the data set a bit more where the information was available. And also the inclusion of the bound compartment that Demetrio talked about meant that we also needed SAF values for those as well. Derek already touched on this a couple of hours back. And he said, as he said, there have been improved energy absorption models available now for particles in the alimentary tract, the gallbladder, and the skeleton. And obviously, the huge data set that they worked on meant that there are changes for all other source target pairs after the move to the voxel phantoms. Another interesting thing, again, Derek talked about the inclusion of blood as a source. Now, this has brought about a change to the limit as energy tends to 0. With blood as a source, it's assumed that the limiting SAF will be the fraction of blood in that target tissue over the mass of the target. So it's a normal SAF calculation, but taking into account the blood in a tissue or organ as well. And this can be important for low energy emitters, because in the past we wouldn't have had that contribution in there at all. So this is something to bear in mind as well. For all other solid source target regions, the SAF limit is just 1 over the mass of the target. Another change, so going back to the human alimentary tract model, and again, this is one of the geometric models. There was quite a big change here, because for ICRP 60, the whole gut wall was considered to be the target, whereas under the since 103, the mucosa layer, there's a specific layer of the target cells. So this this diagram here just shows the layer. This is for the large intestine, and down here you can see sort of the slice through the edge there, and it's 20 microns thick, 280 microns down from the surface. So this means that for some low energy particles, there won't necessarily be absorption into the target layer. So this can considerably change some of the SAFs at lower energies, and can make big differences to the doses. Okay, moving on to biokinetic models. Again, this has been covered by some of my colleagues, but it's worth reiterating here just to draw out the amount of changes that have gone into this set of calculations. So the majority of calculations for the ICRP 60 series employed shared biokinetics. So the radioactive progeny shared the biokinetic model of the parent. OIR and EIR have moved exclusively to independent kinetics. So each member of the chain has its own model. And additionally, all of the biokinetic models now, as you've heard from Rich and from Vlad, are physiologically based, and they involve recycling and excretion pathways where the data is available for that. So that's great in terms of making these models more realistic and extending the use of them, but it also does mean that there will be changes to the dose coefficients. Again, touched on by Demetrio, updates to the lung absorption and clearance parameters, and he gave some examples of how that might impact on the doses back in his talk. And also, this seems fairly trivial in comparison with everything else, but there have been updates to FA values as well, previously known as F1 values. So sometimes that can make a difference too. And with some of the forms given too, some particular elements or chemical forms have been redefined. So when you're doing comparisons of doses, it's sometimes you have to be a bit careful about what you're comparing to make sure it's like for like as much as possible. So as I said, it's a daunting data set, and to try and go through and explain every single dose coefficient would be a mammoth task. And even to try and generalize, because so much has changed, is very difficult too. So what I've decided to do today is just to look at the range of the ratios of new to old for the different types within EIR part 1. So this histogram, and I know it's not a true histogram, but I couldn't get Excel to play ball. So this is showing the results for ingestion dose coefficients, and I've just picked out 3 age groups here: 1 year, 10 year, and adult. And it's reassuring to see that most of them are clustered around 1, so meaning no change to the dose coefficient. You know, we expect to see changes either side with the amount of changes that we've included within the new data sets, and a few outliers too. So that's ingestion. Type F, again, a little bit wider spread here. And of course, once you've got the lung involved, you know, some of these outliers are probably due to the bound state or the increased retention, and it depends so much on the nuclide you're looking at and the half-life of it and the form. So it's really difficult to make generalized predictions about what's going to happen to the dose. But again, majority around about 1. Type M, a bit tighter this time, which is good to see, but again, mostly clustered around 1. And for S, we have a few more outliers, but I think I made a note. I think what have we got in there? I think some radium and some lead. So again, the bound box is being invoked, which tend to push the dose coefficients up. So I know these charts are not going to answer the specific questions that many of you have probably got for your own specific nuclide that you're interested in, but I hope it provides reassurance that overall we are keeping with, you know, that the old dose coefficients were good, and we've improved the modeling, but actually it's not changed substantially because the old assumptions were good in themselves. So I hope that's reassuring, but I have got, oh, and vapors as well, I forgot about those, but again, showing the same kind of trend there in the dose coefficients. So I'm going to just share one example of tritiated water, which everybody always thinks of as being a really simple case. And indeed, it was the first case we started with when we started work on OIR. And I think it took us many months to iron out all of the problems that we found. And I think Rich at the time said he couldn't believe how much we learned from, you know, such a simple example. But so I've put the work of dose in here just for comparison as well. So I've put the inhalation 5 micron, just because that's the 5 micron is obviously the standard for the worker, and you would assume inhalation. We've got an 11% change. For the members of the public, I've picked the ingestion doses just because you would expect members of the public to be exposed more to foodstuffs. So you can see that for the adult, we've got a 6% increase, 10-year-old 17% increase, for the 1-year-old 50% increase. Now, as soon as you start to drill down into this, here I've got the table of equivalent doses. I've put in the weighting factors, although I've not folded those into the dose calculations here at all. But I've got the old and the new equivalent doses here. So you can see that with the old model, it absolutely was uniform across the board, 4.8 e to the minus 11. The new equivalent dose, there's variation in here, and that variation is due to the blood content of those organs. Component here as we had before, and so you can see we've got a fairly big change there, you know, 60%, 20% increases. The problem is trying to unpick it any further. Really, I mean, this kind of tells you all you need to know, that the new model is giving us higher equivalent doses. I mean, this is for the 1-year-old, and that could be due to changes in the masses as well in the reference people. And so I haven't dug any deeper for this particular example. I just wanted to show the sort of rabbit warren you can start to disappear into once you start to pull the doses apart. And I've just picked out a few more examples here just to show the spread of the changes. So this is strontium-90 in diet, ingestion by a member of public. Got the old and new doses, adult, 10-year and 1 year. So you can see for the adult, the dose has decreased a little. 10-year-old, it's increased. For 1-year-old, it's increased a bit more. Iodine 131, all of the doses have decreased. And for cesium 137, again, in diet ingestion, we've got a small increase for the adult, no change for the 10-year-old, and a big increase for the 1-year-old. So trying to draw any kind of conclusion, even for one element or for one nuclide, as soon as you start to look at the different age groups, you've got to really start digging deeper to try and unpick the differences in those doses. But I hope that the things that I've pulled out here, that if you've got any doses of your own that you want to look at, that it will give you an idea of where to start looking to see what sort of things have changed. And there may be a few things that you may not have considered in the past, but maybe there is another candidate as well if you're trying to explain a difference. So that's all from me. Thank you very much.
Thank you very much, Tracy. I propose now to start the last presentation, which will be a demo on how to use the data viewer. As said before, just in the introduction, you have the opportunity either to follow demonstration from Vlad or to download it and to play by yourself with this viewer. You have in the chat the address on where to download the viewer if you want to. Vladimir?
Thank you, Francois. Can you see my screen?
Yes.
Great. So this is electronic viewer, which actually is an electronic annex to OER series and include the full data set calculated for this document and anything which was published as a hard copy and a number of additional radionuclides and dimension of the condition of exposure, which give you the actually anything which you really need or may need. You can download this from ICRP website, and just be careful when you at first time upload it. It's just zip file. You unzip it, and within the zip distribution file will be one more zip. Unzip the second one, and read the README. Usually we skip this part, but it may be important for user, especially corporate users with restricted rights, and with Windows, which has a number of security features and may block help file for opening, and exe file itself also. Just follow the instruction. The file itself, the program itself does not require any installation. Just unzip and put in any convenient folder. Probably just try to avoid any remote location, servers and so on. If the path to the software complex, it may be a potential issue, but the local computer really prefer. As soon as you unzip and run the program, the first screen will inform you about the software itself, who involved, and some additional information how to use it. The help file actually contain all needed references and tips and tricks how to operate the software. And particularly on my screen, you can see that probably it's a little bit tricky. You can see the word Apple up front, but actually it's on my screen now a virtual machine which runs Windows under the Apple. As soon as you start it, you will see these three major tabs: dose per intake, dose per content and reference by assay function, and radium. Let's start from most sexy part, graphs, images, and have a look what we have here. So it's the full list of elements which included in OER series. And here we already have iodine 131. And this series actually just back step, forward step. If you run several types of radionuclides, you can see between in the history list between different radionuclides, because demonstration definitely for a given radionuclide. The graph itself, it's rather interactive, and you can change axis, transfer these presentations, select specific areas, make a zoom, for example, and look on some specific elements of the graphs. And you can auto scale, and here in Legend, you actually can switch on, switch off specific compartments displayed on the screen. Presentation is end user oriented and presented data in the most practical way in terms of aggregated data rather than disaggregated compartments. Such compartments as whole body, you will probably not find it in the biokinetic model, for iodine definitely not, but it's something which is total, gross total. Urine excretion calculated as 24 hours excretions, so it's most convenient for the routine operation, for routine monitoring, special monitoring probably, but as you can see, it's each 24 hours. intermediate data not calculated. Probably later in emergency documents, you will have a little bit more to use spot samples rather than 24-hour samples. Nevertheless, for iodine 131, it's probably not the most important issue. Usually you'll have, if you're doing biopsy, you will do thyroid counter. And as adjusted, you can see it as a table, as a tabulated values with fixed time steps. It's for each radionuclide, these time steps identical. And if you need it for your own purposes, let's say start Excel, you can just easily export it to Excel. This is, can you see Excel? Just copy it to clipboard. And where is Excel?
Yes, Vladimir, we were able to see. Yeah.
Great. So just paste it. Paste the information. It's a very simple way to export the data. Here, the graph itself also will be exported, like you can do it, for example, as a meta file or bitmap. And again, we copy bitmap and paste it here. Interaction between the software and external programs like Excel, Word is really straightforward. You can, for a given radionuclide, you can select type of material. If it's inhalation, it's aerosol diameters. And actually pathway of intake, it could be like this. Each individual data set and data point, you can look on this like this, with specific position of the cursor. And yeah, you can export it as an external file also. You can see. What else here? Just be careful, the asterisk nearby the name of the organ, it actually indicates that it aggregated data rather than compartment of the biokinetic model. Like in this particular case, in thyroid means thyroid plus blood content of the thyroid. And alimentary tract, again, is aggregated alimentary tract content rather than individual compartments. It's for your convenience. If you really have counters, usually have aggregate numbers rather than compartment-related numbers. Well, and you can switch between, currently we're looking at the classical presentation, content per specified dose. You can change the dose, you will see different content. You can see dose per content function. This value which we promote for the interpretation of biopsy data, instantaneous interpretation. And in OIR publication, actually, there is some guideline how to do, even if you have several numbers, several measurements in time. But typically, what you need just, you have a number and just apply this number, you will see your dose. And you see it's just obviously behavior like this, further from the intake, you have more dose per content value. And also you can switch to inverse value, content per intake. So it's technically it's reference biopsy function, which is defined in OIR series. Let's switch to more perspective elements of the assessments. And here we have the list of radionuclides, two subtype radionuclides and materials. If you select radionuclides, you can add any additional radionuclides here. Like, for example, my interest in number of irons, and I will select available irons, put it in this window, and edit. For each individual line, you can change the route of intake. So it could be a mixture of different route of intakes, like inhalation and ingestion. And if it's inhalation, you can change, for example, aerosol diameter. Again, it's easy to copy. Excel file, here, push. There is another presentation. It's material-related presentation when you can select specific material, and this is aggregated. The default presentation like this. You will not see organ doses. Only speaking, for most of routine application, organ doses are really useless. And so this is concept presentation, and you can copy it again somewhere to Excel and use for your own calculations. And disaggregated format include all organ doses, male and female organ doses. On speaking, I don't know for what purposes, because this part, as OIR itself, is substantially about normal operation. We are going, as I mentioned, to produce something for emergency. It will be reference data sets for emergencies, and much more like non-24 hours urine samples, like additional non-routine condition of exposure, non-routine non-reference individuals, and so on. And these parts probably for your curiosity. Again, you can add additional aerosol sample diameters, and table could be really large. If some people even try to add to this radionuclide a list of radionuclides, all radionuclides available, it's possible. Just be patient. If you select all of these guys, it will be several minutes for preparation of data sets. So it will be some pause in the presentation. And radon, again, it's straightforward. You can see the same time and copy, paste available. Actually, that's all. If you try already software, you can ask me any questions.
Thank you very much, Vladimir. I think we are at the end of the session. We are a little bit late on the schedule, but the workshop was supposed to stop right now. What I can propose, still we have a long list of questions. We had to date about 70 questions. Most of them have been already answered. We still have about 15 which are still open, 16 now, 17. What I propose is to take one or two questions and to try to answer directly. What we will do anyway is every question will be saved, and we will answer later by written on this question, so everybody will get his or her answer. The first of question was about the SEF. The question was about our plan to publish the raw data on the SEF, and I guess Derek would like to directly answer to this question.
Sure, and the answer is yes. Publication 133 already has the SAFs for the adults, the male and female adult, and they are freely downloadable from the ICRP and the SAGE website. Publication 155 is in press right now. Once that is published, the SAFs for the pediatric individuals will be freely downloadable via publication 155 on those websites. And for the ease of the user, we are including all of the adult SAFs in that publication 155 download. So the publication 155 download will give you everything you need for all the reference individuals. And there are no changes to the adults from 133. The values are the same.
Thank you, Derek. We also have a question about the revision, the coming ICRP recommendation, the revision of the ICRP recommendation. And the question is about if the revision of the ICRP recommendation will change or not our dose coefficient. So the answer is yes, if ICRP decide to change any weighting factor, the radiation weighting factor or the tissue weighting factor or anything else, of course, that will change the dose coefficient, and we will be asked to recalculate again the dose coefficient. What I could say is that that will be probably a shorter process than it was before, just because we will use the same biokinetic models. It took us a very long time to implement this new model and to derive the new parameter. So in such a case, if ICRP decide to change the weighting factor, we expect that it will take us between 1 and 2 years to produce a new dose coefficient. We have also a question about the interpolation of data. There is two kinds of interpolation. One question about the question from Emmanuel. ICRP provided the rate constant for each age group. For example, for the 5 years age group, were these rates already interpolated from newborn baby? I think, Derek, this is for you. Question from Emmanuel.
Yeah, so if I'm understanding correctly, the question might be focused on the use of a dose coefficient at a given age for an age group, and the part which is slightly different from how a dose coefficient is calculated for a reference newborn, if that makes sense. So let me address the latter first, which is for a reference newborn, we model that intake, and yes, we allow that newborn to grow, right? So we take the newborn through each day essentially of its growth, and as we do that, we are interpolating both the biokinetic and energy deposition parameters, the SAFs and the S coefficients, so that we're modeling that growth. But then that gives us a dose coefficient for the reference newborn and for the reference 1-year-old and the reference 5-year-old. Actually, I should back up and say it's the reference infant, right? I misspoke there. So how those are used, and somebody else can chime in and double check me on that. But how those are used wouldn't necessarily require interpolation. You can apply a dose coefficient for the reference 5-year-old, for example, over an age group without needing to interpolate it. Somebody chime in if you feel like I've misspoken there.
No, thank you. We had also many questions about the use of this dose coefficient for non-reference situation. As an example, we had a question about the use of this dose coefficient for smokers, the use of this dose coefficient for people with no thyroid, and so on. And if I may answer at least part of the question, the coefficients that we are providing are reference coefficient for reference situation and for reference person. They do not apply on specific situations such as a heavy smoker or people with no thyroid. By contrast, I will take the opportunity to advertise on the work of another task group, the TG36, which is led by Augusto Giussani, who is also a member of the TG95 and who is online, but who has no microphone. And he will produce pretty soon dose coefficient for radiopharmaceuticals and for patient, including patient with some difference from the reference individuals. So you will get most of the answer and most of you need from this publication, which will be released in, I guess, 2 years from now. What else? We had also many questions about the use of the default value for the particle. As we say, the reference particle size for the worker is 5 micrometers. For the member of the public is 1 micrometers. All of this was determined, especially for the worker by experimental, experiment. Again, this is reference dose coefficient for reference particle size, but as mentioned and as shown by Vladimir, you can find in the viewer other dose coefficient for other particle size. So usually you are able to extract any information you need. We had also a question that maybe will be the last one because the time is running, about what is behind the soft tissue. We have boxes in the biokinetic model with soft tissue. Rich, would you try to address this question about what is usually in the soft tissue?
I didn't understand the question.
Oh.
Where is it in the Q&A written somewhere?
Yes, I can't remember what is. My understanding, I can't find it, but my understanding is that because we also had this question previously during the public consultation, is what do we put in this box of soft tissue? Does that correspond to every remaining tissue, or
yes, we don't leave out any tissues of the body. If we don't have an explicitly defined tissue, it's contained in other tissue. If the tissue is not explicitly identified in the model, such as liver, kidneys, and so forth, then that tissue is contained in other tissue. Is that what you're asking?
Yeah, I think so.
Okay.
Thank you.
Yeah, we don't. In some earlier ICRP publications, like publication 2, they considered only part of the tissues in the body and didn't deal with the remainder. But nowadays, we deal with all the tissues and all of the biokinetic models, either explicitly or implicitly. And the implicit ones are in other tissue.
Okay. Okay, it's 3:40, so what I would propose is maybe to stop here this webinar, unless some of my colleagues around the table has something to say or something to add. No, nothing to add. Okay, so again, we have too many questions to address today. As I said before, we will try to address every of these questions and we'll provide the written answer. Most of them has already been written and you can probably see them from the chat. We will complete that pretty soon. As I understood also, this presentation was recorded and will be available within few weeks, I guess. I guess also that we will receive a notification from our ICRP colleague as soon as it is ready. And so I think it's time now for me on behalf of all of my colleagues to thank you all for being there today. You were at one time we were almost 500 around the table listening to this to what we have done. So it was really a pleasure for us to share our work and to try to share what we are trying to do for ICRP. I hope you find this this workshop, this webinar interesting, and I hope that it did answer to most of your questions. And I'm looking forward to continue to exchange with you. As you have noticed, every time we produce a document, it is published on the ICRP website for public consultation. So please feel free to comment. This is very important for us. We take every comment into consideration and we try to answer to every comment. So this is true for OIR in IR series, but this is also true for other ICRP publications. So we are really expecting to exchange and to continue to discuss with you with this means. Thank you to all, and hopefully we will talk in another situation. Thank you. Bye-bye.